In April 1950, Baldwin Locomotive Works rolled out something that looked like it belonged in a science fiction movie rather than on steel rails. The experimental locomotive number 4000, nicknamed the Blue Goose, promised to make diesel engines obsolete with the same gas turbine technology that was revolutionizing aviation. For a brief moment, it seemed like the future of railroading would sound like a screaming turbine instead of the rhythmic chatter of diesel pistons. This is the story of an engineering marvel that looked unstoppable on paper, but instead got crushed by American freight railroading. The late 1940s were intoxicating times for anyone who believed in the power of technology. Jet engines had transformed warfare and were about to revolutionize commercial aviation. Gas turbines were spinning up in power plants, promising cleaner and more efficient electricity generation. To engineers drunk on post-war optimism, it seemed obvious that turbines would eventually replace every piston engine on Earth. Westinghouse Electric Corporation wasn't some startup chasing fantasies. They had been building steam turbines for power generation since 1896 and had become one of the world's leading manufacturers of electrical equipment. During World War II, they had developed aviation gas turbines for the Navy, including the J-30 turbojet that powered the Navy's first carrier jet, the FH-11 Phantom. When it came to spinning machinery that generated power, few companies had deeper expertise. The railroad industry was ripe for disruption. Steam locomotives were dying, killed by the superior efficiency and lower maintenance costs of diesel electrics. But diesel technology in 1950 was still relatively primitive. Typical freight road diesels made about 1,500 to 1,600 horsepower, so railroads had to lash multiple units together to haul the heavy trains that post-war America demanded. Baldwin Locomotive Works, once the world's largest locomotive manufacturer, was watching their steam business evaporate, while EMD and Alco dominated the new diesel market. They needed something revolutionary to regain relevance. Partnering with Westinghouse to develop a gas turbine locomotive seemed like the perfect solution. The concept was seductive in its simplicity. Instead of the complex reciprocating machinery of steam or diesel locomotives, a gas turbine would provide smooth, continuous power. No pistons hammering up and down, no connecting rods converting linear motion to rotary motion, no complex valve trains timing fuel injection and exhaust. Just a compressor feeding air to a combustion chamber, with hot gases spinning a turbine that drove an electrical generator. The Baldwin Westinghouse turbine locomotive would produce 4,000 horsepower from twin, 2,000 gas turbines, a single unit output significantly greater than any contemporary diesel locomotive. It would be lighter per horsepower than any diesel engine, and it could burn almost any liquid fuel from expensive diesel to cheap residual oil left over from refining operations. Most importantly, it would give Baldwin a technological edge that could challenge the diesel monopoly that EMD was building across American railroads. The timing seemed perfect. Railroads were flush with post-war traffic and looking for ways to handle increasing freight volumes without adding more locomotives to already crowded yards. In the heart of the Blue Goose, not to be confused with the famous streamlined Santa Fe steam engine a decade earlier, was a pair of massive gas turbines derived from Westinghouse's aviation and stationary power experience. Each turbine was essentially a scaled-up version of aircraft engines, modified for the continuous operation that railroad service demanded. The basic cycle was identical to a jet engine. Air entered through an intake, was compressed to high pressure mixed with fuel, and ignited in a combustion chamber, then expanded through turbine blades that extracted energy to drive the compressor and, in this case, electrical generators. For railroad men accustomed to diesel engines, the difference was fundamental. A diesel engine produced power through thousands of individual explosions per minute, each piston firing in sequence to create pulses of power that had to be smoothed out through flywheels and careful timing. The gas turbine produced power through continuous combustion, with fuel and air mixing and burning in a steady flame that spun the turbine at constant speed. The engineering challenges were immense. Aviation gas turbines were designed to operate at high altitude where thin, cold air provided natural cooling, and where maximum power output was more important than fuel efficiency. Railroad turbines had to work at sea level in desert heat while pulling heavy freight trains at varying speeds and loads. Westinghouse solved the power transmission problem the same way diesel locomotives did. Each turbine drove a DC generator that fed electricity to traction motors mounted on the locomotive's axles. Number 4000 carried two 2,000 horsepower turbines driving DC generators and traction motors. It used 4 two-axle-powered trucks and measured 77 feet 10 inches long. Total weight about 494,000 pounds. Geared for 100 miles per hour and equipped with a waste heat steam generator for passenger train heating. The fuel system was one of the turbine's most promising features. While diesel engines required relatively clean, expensive diesel fuel, the gas turbine could burn almost anything liquid and flammable. Residual fuel oil, the thick, cheap byproduct left after refining gasoline and diesel, cost a fraction of diesel fuel. For railroads moving millions of gallons of fuel annually, this represented enormous potential savings. The turbines could also burn kerosene, jet fuel, or even crude oil with minimal modifications. The Blue Goose incorporated a steam generator that utilized the waste heat from the turbine exhaust to provide steam for passenger car heating, making it suitable for both freight and passenger service. This was an exceptionally efficient application of heat recovery, as early diesel locomotives required a separate, dedicated oil-fired boiler to perform the same function. The exhaust gases, still extremely hot after passing through the power turbines, were ducted through a heat exchanger to generate the necessary steam. Weight distribution was carefully engineered. The turbine locomotive's power-to-weight ratio was superior to any diesel, meaning it could produce more horsepower without adding axle loading that would damage track. This was crucial for freight railroads that were already pushing the limits of track capacity with increasingly heavy trains. The locomotive's streamlined car body wasn't just for aesthetics. It housed complex ducting systems that managed airflow through the turbines and cooling systems for the electrical components. Air intakes were positioned to minimize dust ingestion while providing the massive volumes of air the turbines required. The car body also contained sophisticated filtration systems to protect the turbine compressors from the dust and debris common in railroad environments. Control systems were advanced for the time. The Blue Goose used automatic load control designed to hold turbine speed while generator load varied. Since gas turbines do not operate efficiently across a wide speed range, the electrical controls were more complex than diesel practice and required specialized training for crews and shop staff. When the Blue Goose emerged from Baldwin's Eddystone Works in April 1950, it looked like nothing that had ever run on American rails. The sleek, streamlined design with its distinctive air intakes gave it an unmistakably aerospace appearance that captured public imagination and railroad industry attention. The locomotive's futuristic styling was featured in popular magazines and newsreels, generating enormous publicity for Baldwin and Westinghouse. It ran demos on the Pennsylvania, Missouri, Kansas, Texas, and Chicago and Northwestern, and Westinghouse records mentioned additional test mileage on Union Railroad, Bessemer and Lake Erie, and Pittsburgh and Lake Erie. No orders followed. On paper, the 4,000 horsepower rating looked strong, and the ride was smooth. In practice, part-load fuel burn and throttle lag undercut the pitch. Initial performance tests were promising. The Blue Goose could haul trains that required multiple diesel units, and its smooth power delivery eliminated the jerky acceleration common with diesel locomotives. The continuous torque output meant consistent pulling power regardless of speed, unlike diesels that had to shift through notched power settings. Under load, the ride was smooth and the power delivery was steady. In demonstrations, throttle response lag was noticeable, which made the turbine better suited to steady running than to stop and go work. But even during these carefully controlled demonstrations, fundamental problems became apparent. The turbine's fuel consumption was astronomical compared to diesel locomotives. While exact figures varied with operating conditions, the Blue Goose consumed significantly more fuel than diesel locomotives producing equivalent work. At idle, the turbine still consumed significant fuel just to maintain the minimum operating speed needed to keep the compressors functioning. The noise was overwhelming. Railroad workers and passengers complained about the constant jet engine shriek that made conversation impossible near the locomotive. The locomotives were notoriously loud, exceeding anything produced by steam or diesel locomotives. Maintenance requirements quickly became apparent during the demonstration tour. The turbines operated at temperatures exceeding 1,500 degrees Fahrenheit, requiring exotic materials and specialized procedures that railroad shops weren't equipped to handle. Even routine inspections required cooling periods and specialized tools. The hot section components, combustion chambers, turbine blades, and exhaust ducting showed signs of thermal stress after relatively few operating hours. Despite the impressive power output and smooth operation, no railroad placed orders for production versions of the Blue Goose. The demonstration tour had revealed fundamental incompatibilities between gas turbine characteristics and railroad operating requirements that couldn't be solved with minor modifications. The most devastating issue was fuel consumption at partial loads. Gas turbines are thermodynamically efficient only when operating at or near full power. At the varying loads typical of railroad service, the turbines consumed fuel at rates that made operation economically impossible, even when burning cheap residual fuel. The problem was inherent to the Brayton-cycle that gas turbines use. The compressor had to maintain high rotational speed to provide adequate pressure ratio, regardless of power output. Railroad operations demanded instant throttle response for switching moves, grade crossings, and signal compliance. The gas turbines had significant lag time as the entire system had to accelerate or decelerate together. Engineers found the delayed response dangerous and unpredictable compared to the immediate power changes possible with diesel engines. The thermal inertia of the turbine system meant that power changes took significant time to complete, an eternity in railroad operations. Cold weather operation presented serious challenges that became apparent during winter testing. The turbines required extensive preheating procedures and were vulnerable to ice formation and air intakes. Starting procedures in cold weather could take extended periods, compared to the few minutes needed for diesel locomotives. Diesel locomotives could be started in almost any weather with minimal preparation, a crucial advantage for railroads operating in northern climates. The specialized maintenance requirements were equally problematic. Turbine components required metallurgy and precision manufacturing that few suppliers could provide. The turbine blades were made from exotic nickel-chromium alloys that cost 10 times more than conventional steel. Railroad mechanical departments, already standardizing on diesel technology, couldn't justify the investment in specialized tools, training, and parts inventory for a single locomotive type. Parts availability became a critical concern. While diesel locomotive components were increasingly standardized across manufacturers, turbine parts were unique to each design and required specialized suppliers. Lead times for replacement parts could stretch to months, meaning a failed turbine could be out of service for extended periods. Training costs were prohibitive. Operating the Blue Goose required engineers to understand gas turbine principles, electrical control systems, and specialized starting and shutdown procedures. Maintenance personnel needed training in high-temperature metallurgy, precision balancing, and exotic materials handling. These skills couldn't be easily transferred to other locomotive types, making the investment in training difficult to justify. By 1953, it was clear that the Blue Goose would find no buyers. Baldwin scrapped the locomotive rather than continue supporting the expensive prototype. The company abandoned turbine locomotive development entirely, focusing on conventional diesel designs that were increasingly losing market share to EMD and Alco. While Baldwin's turbine experiment ended in failure, the concept wasn't entirely dead. In 1952, the Union Pacific Railroad began operating a fleet of gas turbine electric locomotives built by General Electric. These massive machines, known as GTELs, gas turbine electric locomotives, would provide the real-world proof of why turbine technology couldn't compete with diesel power. Union Pacific later proved the point at scale with 55 GTELs rated up to 8,500 horsepower. They ran until late 1969 with final retirements in February 1970. The power was real, but the economics weren't. They were designed specifically for the long, heavy freight trains that characterized UP's Western operations, where their high power output could theoretically be utilized efficiently. The first units, delivered in 1952, produced 4,500 horsepower and were followed by increasingly powerful versions as GE refined the design. Union Pacific's motivation was different from Baldwin's experimental approach. UP operated some of the longest, heaviest freight trains in America across the challenging grades of the Rocky Mountains and Sierra Nevada. The railroad needed enormous power to move these trains efficiently, and the turbines offered power levels that would require multiple diesel units to match. For nearly 2 decades, Union Pacific operated these turbines on their main lines, providing the extended service experience that the Blue Goose never received. At their peak, UP operated 55 gas turbine locomotives, making them the only railroad to use turbine power in regular freight service. The results confirmed every concern that had emerged during the Baldwin demonstrations. Fuel consumption remained catastrophic. The UP turbines burned heavy residual fuel oil, a cheap, thick fuel that cost less than diesel, but was consumed in enormous quantities. A single turbine locomotive could consume massive amounts of fuel per hour in heavy freight service, compared to equivalent diesel power. Even with the cost advantage of residual fuel, operating expenses were significantly higher than comparable diesel locomotives. The fuel itself created problems. Heavy residual fuel was so thick it had to be heated to flow through fuel lines, requiring complex heating systems throughout the locomotive. The fuel contained high levels of sulfur and other contaminants that created corrosive exhaust products, accelerating wear on hot section components. Maintenance costs escalated beyond projections. The turbines required specialized facilities and trained technicians that UP had to develop specifically for these locomotives. Hot section inspections required complete disassembly of the turbine, and the exotic materials needed for high-temperature components were expensive and difficult to obtain. UP built dedicated maintenance facilities in Omaha specifically for turbine overhauls. The locomotives were extremely loud, creating noise pollution problems in urban areas and requiring special hearing protection for crews. Exhaust heat was a known issue and made working around the locomotives dangerous in rail yards. The exhaust temperature was so high that it could ignite trackside vegetation and posed a constant fire risk. Throttle lag remained a persistent problem throughout the turbine's service life. Engineers had to anticipate power needs well in advance, making the locomotives unsuitable for anything but long-distance freight service on relatively flat terrain. The instant response that railroad operations demanded simply wasn't possible with gas turbine technology. Environmental concerns also emerged as the turbines aged. The turbines produced visible exhaust plumes and consumed oxygen at rates that could create problems in tunnels. As environmental regulations tightened, in the 1960s, the turbine's emissions became increasingly problematic. The high sulfur content of heavy residual fuel created acid rain concerns that would eventually contribute to the turbine's retirement. By 1970, Union Pacific had retired their entire fleet of gas turbine locomotives, marking the end of the turbine era in American railroading. The locomotives were scrapped or sold for parts, their exotic components making them too expensive to preserve even as historical artifacts. The last turbine ran its final revenue mile in 1969, ending nearly 2 decades of experimental service. The failure wasn't due to inadequate engineering. Both Westinghouse and General Electric had successfully applied gas turbine technology to aviation, marine, and stationary power applications. The problem was that railroad operations, with their constant load changes, frequent stops, and requirement for immediate throttle response, were fundamentally incompatible with turbine characteristics. Diesel engines proved superior in every practical measure that mattered to railroad operations. They could idle for hours burning minimal fuel, then instantly respond to throttle commands with maximum torque, available at any speed. Their fuel efficiency remained reasonable across their entire operating range, and their maintenance requirements could be handled by conventional railroad shops. The parts supply chain for diesel locomotives became increasingly standardized, reducing costs and improving availability. Mechanics could transfer their knowledge between different diesel models, and railroads could maintain unified training programs and parts inventory systems. The economies of scale that came with diesel standardization made exotic alternatives like turbines economically impossible to justify.